Hey everyone, welcome back. We are learning about semiconductors. In the previous lesson, what is a three-terminal semiconductor device? And we also saw the types of three-terminal semiconductor devices. There were two most common devices, namely the bipolar junction transistors BJT and field effect transistor FET. In the previous lesson, we saw in detail about BJT. So in this lesson, I'm going to walk you through field effect transistors. So field effect transistors, as the name suggests, it's very obvious that these are transistors that operate in the presence of electric field. FET is classified into two categories, a JFET and a MOSFET. So JFET is junction field effect transistor and MOSFET is a metal oxide semiconductor field effect transistor. A JFET is further classified into two categories, P-channel and N-channel JFET. So this classification is based on what channel allows the current flow, whether the holes or it's the electrons. MOSFET is also classified into two categories, a depletion type and an enhancement type. An enhancement type allows current flow, where the depletion type restricts current flow. Each of these are further classified into P-channel and N-channel. So this classification is also based on whether the holes or the electron make up the channel for conduction of electricity. Before moving into the types, let's look at the difference between a field effect transistor and the bipolar junction transistor that we looked in the previous lesson. So FETs are unipolar, that is, they conduct current in just one direction. BJTs is very obvious because the full form of BJT is bipolar junction transistor, so these are bipolar. FET is a voltage control device, that is, you can alter the voltage, either increase or decrease the voltage to have a significant effect on the output current. BJT is a current control device. Do you remember that base current could be used to control the output collector current? They have input resistance, which is very high. Here the input resistance is comparatively low. FETs are less noisier. BJTs are more noisy. FET has negative temperature coefficient and BJT have positive temperature coefficient. FET is very costly, but BJT is less cost because these are just back-to-back combinations of diode like PNP BJT or NPN. And FETs have less gain bandwidth product and BJTs have more gain bandwidth product. Now we will look in detail about JFET. So these are transistors that operate in electric field. Take a look at this picture. Now this is a symbol of a JFET. There are two types of JFET, a P-channel JFET and N-channel JFET. So if the holes create the channel, it's called the P-channel JFET, and if electrons create the channel, they're called as the N-channel JFET. Now this channel is created between the drain and the source. Wait 1 second. Do you remember what are the three terminals of BJT called as? The base, the collector and the emitter. Similarly, field effect transistors have three terminals which are called as the gate, the drain and the source. Now the control electrode is the gate. And you also have a semiconductor channel with the electrodes, and drain and source access these electrodes. Here, the gate is present closer to the channel in order to make the electric charge affect the channel. So remember, this is a symbol of a P-channel where the current flow is out of the gate, and in N-channel you have the arrow mark pointing inwards. Now let's look into an N-channel JFET. An N-channel JFET, the channel created is N-type. Now where is this channel? This is a channel that connects the source and the drain. Because source and drain is not directly connected, you need a channel through which electrons will be able to flow, creating conduction. So depending on what is the majority carrier of this channel, we have N-channel JFET and P-channel JFET. So now we're looking into N-channel JFET where electrons are the majority carriers. Now when we apply a positive voltage across the drain and the source, the electrons flow from source to drain. Now what does that mean? That means the current, output current, which is called as the drain current, is produced from drain to source. So, when I apply a positive gate voltage, you have a current flow. Now, what happens when I apply a negative voltage? So, when I apply negative polarity at the gate, the depletion region is being created. Now, when depletion region is created, the channel width decreases. Now, once the width of this N channel decreases, what happens is now all the charge carriers start to collide with each other, so there's more resistance for current flow. And as a result, there's no current flow in the device when I apply negative voltage at the gate in N-channel JFET. Now this is the same in a P-channel JFET, with a little difference of course. Now the channel here is a P-type instead of an N-type. Now when I apply a negative voltage across drain to source, you have a current flow from source to drain. But in N-channel, we had a positive voltage that creates conduction. But in P-channel, we have a negative voltage that creates conduction of electricity. So now what happens if I apply a positive voltage in a P-channel JFET? The same happens. That is, when we apply positive gate voltage, the depletion region increases, so the resistance also increases and the channel width decreases, preventing current flow in the JFET. Now, we'll look into the next type called as the MOSFET, the metal oxide field effect transistor. Now this is a field effect transistor with a metal oxide layer. Now these MOSFET also have the same three terminals, source, gate and drain, along with an extra terminal called as the substrate or the body. Take a look at this picture. This is an example of MOSFET. So we have the gate, drain and source, and these are the metal layers, and this blue color over here is a silicon dioxide layer. Let me zoom in for you. So now these are also of two types as we saw, N-channel and P-channel. It's the same. Whether the holes or the electrons create the channel determines the type. So we have silicon dioxide layer and a metal layer over here. Now why do we use silicon dioxide layer over here in a MOSFET? Now this is because silicon dioxide usually insulates or isolates the metal from the semiconductor. Do you remember that we saw Schottky diode? It's something more like that, except that a Schottky diode is 2-terminal and a MOSFET is a 3-terminal device. So we don't want the charge carriers in the gate and the semiconductor to recombine with each other. We just want a channel to be created. We don't want them to combine with each other and become stable or cause current flow. So we just want a channel between the source and the drain so that the electrons could move from drain to source or source to drain. And that is the reason why we use a silicon dioxide layer over here, which isolates them from getting in contact with each other. MOSFETs are further classified into two categories, an enhancement MOSFET and depletion MOSFET. So an enhancement MOSFET is also referred as normally off transistors, and depletion MOSFET is normally referred as the on transistors. Here, the voltage is applied to the gate at least equal to the threshold voltage. Now when you apply a voltage that's equal to threshold voltage, you try to create a conduction path between source to drain and you make the current flow. But in depletion mode, when you apply a voltage that's almost equal to the threshold voltage, you're not creating a conduction path, but instead we're destroying the conduction path that exists between the source and drain. And because we distract the conduction path, we prevent the current flow in depletion mode. Now let's look into enhancement mode MOSFET. Now take a look at this picture while I explain. Now this is similar to an open switch, and it requires a gate source voltage in order to switch on the device. Here the applied gate voltage enhances the current flow, whereas in depletion mode the applied gate voltage will prevent the current flow. Now when I apply a negative gate voltage, what happens? It's a negative potential over here which attracts the positive holes in the p-type substrate and creates a p-type channel between the source and the drain. So the holes accumulate at the top, creating a new channel. So now when I keep increasing the gate voltage that I apply here, what happens is that the channel width keeps increasing and so the conductivity also increases. Thus, if I apply a negative voltage, I'm creating a P channel here. So if I apply a positive voltage, I'm going to create an N channel. So that are the types of enhancement mode MOSFET. Now let's look into a depletion mode MOSFET, which is just the opposite of enhancement mode MOSFET. So here it is considered as a closed switch, and here you need a gate source voltage to switch off the device. In enhancement mode, we needed a gate source voltage to switch on the device. Now they are on even at a zero gate voltage. But a depletion mode has lesser conductivity when compared to enhancement mode because here we're trying to disrupt the channel that's being created between source and drain, ensuring that there's very less current flow between source to drain or drain to source. And the types of depletion mode are same as enhancement mode. There is N-channel depletion mode and P-channel depletion mode. So if the channel created is holes, then it's a P-channel depletion mode. And if the channel created is due to electrons, then it is N-channel depletion mode. Yeah, so we've come to the end of the lesson. Now let me summarize what we saw in this lesson. We saw about field effect transistors. We saw the types of field effect transistor, that is, a junction field effect transistor and metal oxide semiconductor field effect transistor. In JFET, we saw it is of two types, P-channel and N-channel, and in a MOSFET, we saw a depletion type and enhancement type. And each of these types are further classified into P-channel and N-channel respectively. So in the next lesson, we will be moving on to 4-terminal semiconductor devices, having 4 terminals through which current can either flow in or flow out of the semiconductor device. Well, thank you for watching and stay tuned for more. If you have any queries, please ask me in the comment section below.